Welcome to section 7.2, Identifying Functions from Graphical Patterns. At the end of this section, we should be able to answer these questions. What are the visual characteristics that allow us to determine the type of function from a graph? What information from a graph is necessary to solve for a function's equation? How do we solve for the equation of a function given a graphical image? And finally, what are some real-world examples of each type of function discussed in this section? To answer the first question, let's take a look at what the basic graph for each type of function looks like, and then how that graph can be transformed, and what the equations would look like once the equation is transformed. Let's start with the most obvious, the linear function. The most basic linear function is y equals x, and as we can see, it goes through the origin and increases at a regular rate across all real numbers. The general equation that many of us are familiar with, y equals ax plus b, and the transformed function, where we look at horizontal and vertical translations and additional dilations, looks like the point slope formula that we're all familiar with. Y minus y1 equals a times x minus x1. And here are various examples of our transformed function and what it can look like. We can increase the slope and shift upward, or we can make the slope negative, flip the graph, and then translate it vertically. Our next function is the quadratic function. The basic quadratic function, y equals x squared. We're all familiar with the graph or equation y equals ax squared plus bx plus c. And finally, we have the vertex form, which shows the specific translations and dilations that we've applied to the parent function. Y minus k equals a times x minus h quantity squared. Our basic graph is concave upward, increasing on both sides from the vertex at the origin. We can translate upward and horizontally to the right, as we can see here, and then dilate, make the graph thicker or thinner. We can also flip the graph by putting a leading negative coefficient on our x squared term. Our next set of functions are the power functions. Here the basic graph is basic equation is y equals x to the b. Our general equation would allow some dilations. And finally, our transformed function allows both dilations and vertical and horizontal translations. We have three possible scenarios in a power function. We can have our power, our b value, be larger than 1, in which case our graph will go through the origin and increase with a concave upward shape, concave up. If our b value, here it's 0.6, is between 0 and 1, then our graph still increases as x increases, but the shape of the graph is now concave down instead of concave up. And again, the graph still goes through the origin. If our b value, or our power, is less than 0, we have a negative power, then we can see that the graph does not go through the origin. In fact, we have an asymptote at x equals 0 along the y-axis, and the graph also has a horizontal asymptote along the x-axis. So the graph doesn't go through the origin. It decreases and is concave up throughout its entire domain in the first quadrant. Our last graph is the exponential function. And here, the graph is y equals b to the x. Notice how the x is in the exponent. The general equation allows dilations, y equals ab to the x. And the transformed function would be ab to the x plus c. Our basic graph increases just like the power function when b is greater than 0. And is concave up, but the graph doesn't go through the origin. In fact, the graph is going to go through either 1 if the graph hasn't been dilated, or through A here if the graph has been dilated. If our base, is greater than 1, we see this shape concave up. If our base is less than 1, as it is here in the second example, our base is 0.7, we see that our graph is decreasing across its domain and concave up. And then by applying a negative sign in front, we can flip the graph and see how the graph would be decreasing and concave down instead of increasing and concave up for a base larger than 1.